Okay, this is video for Project Test 7, video number 4, and it's problems 31 to 40. A news organization conducted a survey about preferred methods for obtaining the news. A random sample of 1,605 adults. We have it as 1,605. I'm going to write that down. It equals 1,605. Living in a certain state was selected, and 16.2% of the adults in the sample reported that television was a preferred method. So P hat equals 16.2. Which of the following is an appropriate margin of error for a 90% confidence interval to estimate the proportion, to estimate the population proportion of all of adults living in the state who would report that television is their preferred method? So first off, let's write the formula for the confidence interval. So P hat plus or minus Z star, P hat, Q hat, and N. All right, so we know that P hat is going to be 0.162. 1 minus that, 1 minus 0.162 is Q hat. We know our sample size is 1,645. And then we need to calculate our Z star. And since we are calculating a 90% confidence interval, we'll use 0.90 as our area. So second bars, inverse norm, parenthesis, 1 minus 0.90, close parenthesis, divided by 2. Mean of zero, standard deviation, oops. Mean of 0, standard deviation of 1. We end up getting 1.645. And I only worked with this part of it because this part represents the margin of error. So 1.645 times 0.162 minus this. And when we're looking at number 31, we are looking at A as our best answer. Okay, moving on to number 32. Number 32, this is one of those questions where you better read very carefully. And this is just an encouragement to do so during the test. A fitness center offers a 1-month program designed to reduce body fat through exercise. The table shows the body fat percentage before and after completing the program for 10 randomly selected partners. Now I see before and after, and I immediately think, hey, we have a before and after. We have each one measured twice. This is probably going to be a matched pairs. This is what I'm thinking this is going to happen, but I better read continue on because I'm going to find out they're tricking me. The director of the program wants to investigate whether knowing the body fat percentage before beginning the program can help predict. The only type of problem that we work with for prediction is linear regression. So although it looked like this was going to be a matched pair, this appears to be going to be a linear regression. Which of the following procedures is the most appropriate? Well, we already said it was for prediction, so matched pairs is not it. A 2 sample is not it. A 2 sample Z is not it. Chi-square is not it. And the very last one happens to be linear regression. If you did not catch the word predict, you probably marked A, and I totally understand that, but this is why it's really important to read the questions all the way through, because they do some things on here to try to trick you, and that's one of them. Number 33, a recent survey estimated that 19% of all people living in a certain region regularly use sunscreen when going outdoors. The margin of error for the estimate was 1 percentage point. So basically we have 0.19 plus or minus 0.01, which tells me that I have an interval from 18 to 20. And whatever my confidence level is, these values, anything between 18 and 20, I consider to be reasonable or plausible. So approximately 1% of all people living in the region were surveyed. No, that's not what the margin of error is. Between 18 and 20% of all people living in the region were surveyed. No. We're 95% confident, or whatever, confident that the true population proportion regularly use sunscreen. All possible samples of the same size will result. No. We can't have confidence in the endpoints. All possible samples of this size, we believe will capture it, the true population. The probability, we don't like probability when we're talking about confidence intervals. It is plausible that the percent of all people living in the region who regularly use sunscreen is 18.5%. And yes, 18.5 lies within that interval, so that is plausible. It may or may not be the answer, but it is definitely plausible. And because it's plausible, that is the only true statement that we have for this one. All right, moving on to problem 34. According to a recent report, customers who shop at a certain online store spend an average of $1,500 a year at the store. To investigate whether the mean amount spent was greater than the reported average, an economist obtained the mean and standard deviation of the amount spent in the past year by a random sample of 120 customers. So basically we have n equals 120. We have a null hypothesis that mu is 1,500. And the alternative is mu is greater than 1,500. With all the conditions for inference met, the economists conducted the appropriate hypothesis and obtained a p-value of 0.25, which is a statement is the most appropriate conclusion for the investigation. So we have a p-value of 0.25, and if we have an alpha of, let's just say, 0.05, this is greater than that, so we're going to fail to reject. So it does not appear, so we're going to fail to reject the null, which means we do not have sufficient evidence. So we start off, there is convincing, no, there is not. There is convincing, no, there is convincing, no. There is not convincing, better keep reading. Statistical evidence that the mean amount of money spent each year by all customers who shop at the store is greater than 1,500. And by the way, they say by all customers. When they use the word all, this is the true population. They're saying that all customers, the true population. So all of them. So that sounds pretty good, like D. There is not convincing evidence that the mean amount of money spent by each year by any sample. No, we're not talking about the sample. We're talking about all customers or the population. So the best answer for 34 is D. Number 35. Scientists working for a water district measure the water level in a lake each day. The daily water level in the lake varies due to weather condition and other factors. The daily water level has a distribution that is approximately normal with a mean water level of 84.07 feet. So we have a mean of 84.07. The probability that the water level in the lake is at least 100, so in other words, up here at 100 is 0.064. So they're telling me this area right here is 0.064. And I'm going to go ahead and subtract that from 1. So 1 minus 0.064 is 0.936. And that means that this area back over here, and shaded in green, is 0.936. This goes to negative infinity, and this goes to positive infinity. Which of the following is the closest to the probability that on a randomly selected day, so one day, the water level in the lake is at least 90? So first off, let's start working with what we have. We'll come back to the at least 90 in just a moment. So Z equals X minus mu over sigma. And I have, in this case, what do I know? Well, I know my mean. I have a mean of 84.07. I'm missing a standard deviation, which kind of makes things a little bit rougher, but I have an X value of 100. So if I can get a Z-score, I probably can find out what my standard deviation is. Well, they give me an area of 0.064, which means working from left to right, I have an area of 0.936. So I need to calculate a Z-score for this 0.936. So second vars, inverse norm, 0.936, because I work left to right. And I end up getting a 1.522 for a Z-score. (100) minus 84.07 equals 15.93. So I have 1.522 equals 1.53, 15.93 over sigma. If I multiply by sigma, then divide by 1.522, take this number, divide it by 1.522, divided by 1.522, I end up getting a standard deviation equal to 10.466. That's great and all, but that's not what they asked me for. They said, what's the probability that on a randomly selected day, the water level will be at least 90 feet? So I want the probability that X is greater than 90. Well, guess what? I still have the 84.07, and I want to know the probability that it's 90 or more, but I know my standard deviation is 10.466. So basically, at this point, I want the probability that Z is greater than 90 minus 84.07 over 10.466. Now I can do this very simply as a normal CDF. So my lower bound is going to be 90. My upper bound is going to be positive infinity. My mean is 84.07, and my standard deviation is 10.466. So this is my lower, this is my upper, this is my mean, and this is my standard deviation. So let's go ahead and plug this in a calculator and see how this all works out for us. Second vars, normal, CDF, lower bound 90, upper bound infinity. 84.07, standard deviation 10.46, and I end up getting 0.2853. All right, and my closest answer to 0.2853 is going to be A, which is 29. And by the way, there's oftentimes a lot of rounding, and so you're going to have to be really careful on these because sometimes you won't see your exact answers. And obviously I didn't see my exact answer there. Okay, so I had to solve first. First thing I did was solve for my standard deviation. Once I found my standard deviation, I could just do a normal CDF, and there we go. We would need to show this if it were FRQ, but if it's just multiple choice, you can go just straight to the normal CDF. All right, number 36. The president of a large company recommends that employees perform on average 24 hours of community service. All right, so they're wanting 24 hours of community service each year. The president believes that the mean number of hours of service performed last year was different. In other words, that it was not equal, It was a two-tailed test from the recommended 24. To estimate the mean number of hours of community service performed last year, the president obtained data from a random sample of employees and used the data to construct a 95% confidence interval. So here's our interval, it's a 95% confidence interval. So we're 95% confident that the true population mean number of service hours lies within the interval. Notice the claim was 24 and it's not in the interval. So if all conditions for inference were met, does the interval provide convincing statistical evidence at a alpha equal 0.05 to support the president's belief that the mean number of hours is different from what was recommended? Well, this was a 95% confidence interval, so they're asking for an alpha equal to 0.05. Now let's take a look at this real carefully to make sure that we're good. We have 0.95. 1 minus 0.95 equals 0.05. So, and that's our area in the tails. And sure enough, we have 0.025 here, and we have 0.025 here. So we have an alpha level of 0.05. All right, so we have that we are consistent with that. Yes, the interval supports the president's belief because 0 is not contained in the interval. We're not concerned about 0, we're concerned about 24. So A is wrong. Yes, the interval supports the president's belief because 24 is not contained in the interval. This is our correct response. All right, we have enough evidence because our bound was 20.37 to 23.49. 24 is not in the interval, so we can say that the president is correct. It was different than 24. In fact, it was less than 24 hours of service on average. All right, this one right here, number 37, I'm not even sure they should have included this because it's not in the textbooks. And truthfully, it's a little bit different than anything else that they've ever given. But we will go over it. The other thing that I don't like about it is they used a substantial amount of rounding. And so it makes this problem a little bit ugly. So in other words, this is one of those problems that it's like, if it doesn't make 100% sense to you, don't worry, don't stress it. You can still make your 5, even if you never understand this question. So an international polling agency estimates that 36% of adults from country X were first married between the ages of 18 and 32, and 26 from country Y were first married between the ages of 18 and 32. So X is 0.36, Y happens to be 0.26. So this is their claim. This is what we believe. And this is P for X and P for Y. Which of the following is the closest to the probability that the difference in proportions between a random sample, so if we take a random sample of 60 adults and a random sample of 50 adults from country Y who were first married is greater than 0.15. So we want the probability that P hat X minus P hat Y is greater than 0.15. Wow. Okay, so this is a bit complicated. So first off, this is what we believe. So what we believe is this. We believe our null hypothesis is that Px minus Py equals 0.10. That's what we believe. And we want to know what's the probability that we'd get a sample like this. So this is going to be a very, very unattractive formula and a little bit different than what we've always worked before. So P hat X minus P hat Y, and I'm going to put that in parentheses. That part's not so different. Minus, normally it's a 0, so we don't ever include it because we've normally had a 0 there, but here we don't. Here we have a 0.10. That's our difference. over P hat combined, Q hat combined, N1 plus P hat combined, Q hat combined, N2. Well, remember, the combined ones we have to pool. So, which means we're going to have P hat combined equals X1 plus X2 over N1 plus N2. Well, they made this awfully difficult as well because we're going to have to round, and they were very, very ugly in the way they did this. So we have X1, we had 36%, and we have a sample of size 60. So if I multiply 0.36 times 60, I get 21.6, and I'm going to let you know they're going to truncate. All right. So we're going to go ahead and truncate because that's going to give us closest to the reality of what they had. I don't agree with that, but that's what I would have rounded up. But either way is fine. You're going to be close enough to the answer. So 21 over 60 plus, and the way I did that real quickly is we have, all I did was go 0.36 times 60. Well, the next one is 0.26 times 50, which gives me 13 over 50. So that ends up giving me 21 plus 13 is 34, 60 plus 50 is 110. So 34 divided by 110 equals 0.31. All right, equals actually 0.309. So P hat C equals 0.309. Q hat C equals 1 minus that, which is 0.691. All right, so 0.691. So now I can go ahead and plug in to this. And we know that they want this difference right here to be 15%. So my numerator is going to be 0.15 minus 0.10 because they're looking for a 15% here. We're expecting a 10%. And now we have 0.309 times 0.691 over 60 plus 0.309 times 0.691 over 50. And by the way, this is not one you can go straight up and do on the calculator. Well, the numerator is nice and easy. We end up getting 0.05. The denominator is going to be a bit more challenging to work with. So here we go. 0.309 times 0.691 divided by 60 plus 0.309 times 0.691 divided by 50. And I need to take the square root of that number, caret 0.5, and I get about 0.0884. So I end up with 0.05 over 0.0884. And by the way, we're calculating a z-score because we're working with proportions. So my z-score, so 0.05 divided by 0.0884 equals a z-score of approximately 0.57. We can use the 0.565, that's fine, but I'm going to go ahead and round it to 0.57. So second VARS, and since I have a z-score, now that I have a z-score, I can do a normal CDF. All right, with the Z-score, my mean is 0. This is a positive 0.57. So I want to know what's it like to be more extreme than that. So second VARS, normal, CDF, lower bound, 0.57, upper bound, infinity, mean is 0 because it's a Z-score, standard deviation of 1. And second VARS, normal CDF, 0.57, not 57. And I end up getting 0.2843. And after all the rounding that I did, I end up getting to their answer. Okay, I don't approve of this particular problem, but please notice what we did, and I'm going to start real quickly walk you through what we did here, is they said that they wanted a difference of 15%. So P hat X minus PY needs to be 15%. Well, what the initial belief was, it was 36 minus 26. So they initially believed it was 10%. So that gave us 0.15 minus 0.10 gave us a difference of 0.05 in the numerator. Because it was a hypothesis test, I needed to combine them. I needed to get a P hat combined. And so I went, and we know it was like, well, we have 36%, 6% of 60. 36% of 60 is about 21. And 26% of 50 is 13. So that's where the numerators came from. And when I did this, I get 0.309. So that gives me my P hat C and my Q hat C. And then when I solve it out, I ended up here. Tough problem, don't stress it. And if you do have questions about it, I'll be more than happy to answer them to the best I can. All right, number 38. A consumer group wanted to investigate the relationship between the number of items purchased at a single visit to the local grocery store and the total cost of the items purchased. The group obtained a random sample of 11 receipts, this is going to be important, from the store and recorded the total number of items and the total cost from each receipt. The computer output of an analysis of the total cost versus number of items purchased is shown in the table. Assume all conditions for inference are met. Based on the results shown in the table, which of the following is a 95% confidence interval for the average change in total cost for each one item of purchase? So basically, they want to know cost over number of item for each one number of item. Now, obviously, what this means is we're working with the slope. And our slope in this case is 2.784. So we're doing a confidence interval for the slope. So it's basically B hat plus or minus T star times the standard error. Well, that means we're looking at this right here because this is the y-intercept. That constant is the y-intercept. So we have 2.784 plus or minus. We'll come back to T star in just a moment. We have a standard error already calculated out. So it's going to be 0.2265. And by the way, that gets rid of the last three. So now we need to calculate our T star value. And we're working with a 95% confidence interval. Please don't forget with regression, degrees of freedom is n minus 2. So in this case, 11 minus 2 equals 9. So second VARS, inverse T, parenthesis, 1 minus 0.95, close parenthesis, divided by 2, degrees of freedom is 9. And we end up getting 2.262. 2.262. That's this value. Our answer is B. The other thing is that 12.29 wasn't very reasonable to begin with. Okay. Moving on to number 39. A doctor uses a new diagnostic test to indicate whether a patient has a certain disease. The doctor will prescribe medication for the patient if the doctor believes the patient has the disease as indicated by the diagnostic test. The situation is similar to using a null hypothesis and an alternative hypothesis to determine whether to prescribe the medication. So if I believe this, if I believe the patient has the disease, they get the medication. So if I believe the alternative, they get the medication. Which of the following describes the power of the test? Remember, power equals correctly rejecting a false null. All right? So power, that means we were rejecting the alternative. And we believe the patient has the disease and we're correct. As a result, we're prescribing the medication to a patient who has the disease. In other words, power is doing the right thing, but it involves rejection. The probability that the new test is better than the older test, no, that's not power. The probability the new test indicates the disease in a patient who has the disease. It indicates they have the disease and they do. This looks pretty good. I'm liking B. The probability the new test indicates the disease of the patient who does not have the disease. No, that's an error. The probability that the new test does not indicate the disease in a patient who has the disease. Once again, that's an error. Power is doing the correct thing. It's correctly rejecting. The probability that the new test does not indicate the disease in a patient who does not. And yes, that is a correct decision, but we have to correctly reject, and that would not be rejecting the null. So this is wrong. Our best answer is B. So 39 is B. All right, on to problem 40. To investigate the relationship between age and preference for two mayoral candidates in an upcoming election, a random sample of city residents was surveyed. The residents were asked which candidate they preferred, and each resident was classified into one of three age groups. So basically, so we have three categories. The test statistic for the appropriate hypothesis test was 3.7408. Approximately, what is the probability that the observed responses would be as far or farther from the expected responses if there is no association? Right there, they're telling us association. That means they're doing a chi-squared test of independence. And they're asking us for a p-value. How did I know that? Would be as far or farther from the expected value. So I need the p-value of a chi-squared. That's what they're asking for. Well, with a chi-squared test of independence, I'm going to need a couple things. One, I'm going to need a chi-squared value. They gave it to me. Chi-squared is 3.7408. But I also need to know my degrees of freedom. Well, in this case, I have two candidates. And I have, so candidate 1, candidate 2, and I have three age categories. Age 1, age 2, and age 3. Now, for this particular problem, for chi-squared independence, it's row minus 1 times column minus 1. That's my degrees of freedom. Well, my rows is going to be 2 minus 1, and my columns are going to be 3 minus 1. This is 1 times 2. So I have 2 degrees of freedom. My degrees of freedom are 2. Now I can go back to the calculator here, and it has a chi-squared. Second vars chi-squared CDF. My lower bound, 3.7408. My upper bound is infinity. And by the way, the upper bound for the chi-squared will always be infinity. And my degrees of freedom is 2. And I end up getting 0.15406. And my closest answer is 40, for 40 is B. All right, I'm going to do one quick thing real quickly. I'm going to look back at number 39. We said power of the test was correctly rejecting a false null. Let's look at a couple of these others. The probability that a new test indicates the disease in a patient who has the disease, that's doing the correct thing. The probability, looking at C, the probability the new test indicates the disease in a person who does not. So I rejected this and I believed this, but they said it was an error. So this would be, I rejected, so this would be a type 1 error. Over here, the probability the new test does not indicate the disease in a patient who does have the disease. So this is true, but I failed to reject. If I failed to reject, this would be a type 2 error. All right. Okay, thank you for bearing with me. And when I went back to that, I hope this was helpful. And that'll conclude this video.